Hey, how y'all doing? If you said something, Paulo, I did not hear it. I'm hoping that one of you will unmute. I checked my mic earlier and, says it's working.
Hello. Hello.
Okay, now we can hear y'all. Excellent. So, hey, maybe it's just time to do what we normally do and it will be good. Uh, the only thing that really bothers me about these Zoom classes is like this little Zoom bar which shows, the audio, the video, the chat, like you click on this or that. It has to be floating somewhere on the screen, but I want to use like 100% of the screen for other purposes. So if that's like the biggest complaint I have in life, my life's going really pretty well. Hopefully your day is going well, or right, at least as well as mine is. Maybe just jump right into it. I think the announcement I have is if you are able to be in San Luis for the final, that's the plan. If you have chatted with me already about, oh yeah, I've got a guy who can proctor the exam, you know, uh, it has to be worked out. Can't just be last minute, your buddy Fred. It has to be someone that I can like track down on the internet as a legitimate, real human who's working in a position where they should, in theory, follow instructions from me, like a faculty member at another university, a community college, a librarian that you're not related to. That sort of situation always works out brilliantly. I've talked to about three or four of you who need to use this. If you haven't chatted with me yet and you think possibly you're going to want to try and work something out, get on it and get hold of me via email right away, and then we'll follow up, make sure everything's good. Second thing I wanted to say is I'm thinking I'm done with the exam, but I'm not done 100% with verifying that every single student uploaded answer is something that I've scanned over and incorporated into my awarding of partial credit. So just hold off another day until you think it's final. But when I do put up answers to the exam online, like I did for the first exam, that's what I'm saying. Your score is final. Of course, you're welcome or even encouraged to argue with me. Not that I want to have arguments over points, but usually in the process of discussing, hey, hold on, how come I didn't get full credit? A student is able to learn something differently, or maybe I'll learn I made a mistake and I should have given more points. So it's always a good outcome. Either learning happens or more points are typically awarded. It's probably about 19 of one, 5 of the other, but it's still time well spent. Ask yourself on the exam on any points you didn't get fully correct. Hey, is my answer really close to what is listed as a reasonable and proper answer? Okay. So I want to mention that there's also homework assignment due out of chapter 7 due to tomorrow night. And the problems out of the first two sections of chapter 7, you might want to ask about those right now in class before we move forward. So that's up to you. Anyone want to ask about any of those problems in 7.1 or 7.2?
I had a question from yesterday's lecture.
Yeah, yeah, love it. What?
I'm a little confused about what alpha means and like what the purpose of
Okay.
it is.
Okay, I love it. Great question. I said quickly, and I think that's the nature of the question is like, hey, what is this thing alpha? Alpha is the rate of error. Okay, so let's go. Alpha is the error rate. Now, typically, I'm going to say 0.05. So 5% of the time, if we're using a confidence interval, we would get an error. And now, like we talked about yesterday, you don't know on any particular trial of the confidence interval procedure whether you made a mistake or not. It's based on how often the data would be unlucky, if you will, so unlucky that your population mean mu is not inside the confidence interval. And so if we typically go with a 0.05 error rate, the typical confidence interval, the 100 times 1 minus alpha percent confidence interval for the unknown population mean mu. Well, if alpha is 0.05, that's going to be corresponding to 95%. Okay, so a 95% confidence interval for mu is one which, if we follow the procedure, will correctly capture mu some 95 out of 100 times in the long run. And that procedure, as we note from yesterday, is X bar plus or minus 1.96 times sigma over the root of n. And I'm going to sort of switch gears just a little bit and say, well, we don't usually know sigma. So I'm going to actually write in, instead of sigma, I'm going to put in uh, S over the root of n. And that's valid if n is big. And by big, geez, that's a philosophical argument. I'm going to say 30 or more, or, 100 or more. Some people go with 25 or more. Essentially, large enough such that the sample standard deviation sigma is going to be pretty darn close to the population. The sample standard deviation S would be pretty darn close to the population standard deviation sigma. So 30 or so. So I think, Meg, that's addressing your question, but I would love it if you'd follow up.
Yeah, just another question about it. So when we don't know
Yeah.
the Z value, why do we do alpha divided by 2 for the Z value?
Okay. So the term more generally, and so maybe I'm going to replace this with a more general version of the equation, uh, is going to be with, like you noted, Z with alpha over 2. Why alpha over 2? Well, alpha O is the error rate, so think typically 0.05, and Z alpha over 2 is the Z value that corresponds to exactly alpha over 2 in the upper tail. And so I guess because of the symmetry of the normal curve, negative Z alpha over 2 is going to also have that same rate of error, alpha over 2, down there. So if we go the plus or minus that amount, we're going up and down the same distance, the distance being sometimes termed the standard error, the typical amount of error in X bar when used to estimate an unknown population mean mu. So why alpha over 2? Just a way of noting things. Z with a subscript corresponds to the Z value with that lower tail area. I mean, sorry, with the upper tail area corresponding to that rate. So alpha over 2 says the error rate split into two parts. One half of alpha, one half of the error rate is in that upper tail. So, Meg, did that get to your question?
Yes, thank you.
And do you want to follow up on that at all?
No, I'm okay.
Anyone else want to follow up on that? Because I love the topic.
Right there where you put if n, what did you write to right after if n?
If
Big?
n is big,
Oh,
large, more than 30 or so.
okay.
Yeah,
I
yeah.
see.
My font, my handwritten font is really pretty bad. I should never try and copyright it because no one would ever use it. Okay, so there's something that I wanted to mention yesterday, and it completely drew a blank, and I didn't get there in my own brain, so we didn't do it. And so let's finish up one thing in chapter 7.2. And that really is the question of, well, what if you do a confidence interval and your margin of error, the plus or minus amount, is much larger than what you're happy with? What could you do to get a smaller margin of error? Our procedure, and I'm going to go with the 95% confidence because that's just what people do. X bar plus or minus. I'm going to write as 1.96 times S over the root of N. Again, N is big. Again, think 30 or more. And I'm going to sort of, just for the sake of my own math here, I'm going to write that as, uh, I'm going to write that instead of 1.96, I'm going to write that as 2. It's just easier to remember 2 than 1.96. Okay, honestly, I remember 1.96. I've remembered it since the 80s because I started doing this stuff when it was the early 80s. Oh, geez. Whatever. The point is, moving on. I've been 40 freaking years. Okay, so moving on. I'm going to use plus or minus 2 in my own brain a lot of the time. And that's something that John asked right at the very end of class yesterday. Should we use 1.96 or should we use 2? If you're using a Z-based confidence interval, 1.96 is a little bit more precise, but it's so darn close to 2 that if you used 2 instead, when I'm grading the final exam, the student who gets 1.96, if I do want to sort of like be really anal retentive about it, they'll get like 6 out of 6 points on a problem. And the person who writes 2 will probably get 5 out of 6, or maybe the full 6 out of 6 points. 2 is about 95% confidence. We know this. And the people who say you got to be really precise, there's other things that are bigger issues in life. One of them is the choice of S here, because S itself varies around the actual population standard deviation sigma by enough that you're saying it's probably a bigger deal than the 2 is. So X bar plus minus 2 S over root N. If you have a target margin of error that you want, I guess what we could do is maybe solve for that N. I guess if you want a plus or minus that's equal to some target margin of error that I always call E. E is your target plus or minus the target margin of error, the target amount by which you're willing to be off with some 95% confidence. E here is 2S over root of N. If we're solving for N, I guess root N here is 2S over E. And if I square everyone in sight, N should be equal to 2S over E, whole thing squared. So if you tell me the target margin of error, E, good. If you tell me 2, again, good. We can deal with that. S, okay, what about S? S is the standard deviation that I will be getting in my new, larger sample size worth of data. So we don't know what S is until you actually set the sample size N and then go collect the data and then calculate the S. So what should I be doing? Okay, here's our practical answer. You probably don't know what S will be, but you probably have an earlier sample, right? That you can work with. It had a standard deviation S. Or perhaps there's a range of standard deviations that someone told you, oh, the plausible range is 0.8 to 0.84. And so go with the larger S in the range of what's plausible. Okay. So take an educated guess or ask an expert in the area. And what we're trying to do is essentially get something for the right-hand side so we could then determine the value that we ought to be using for N. But if I tell you, here's the target margin of error, and here's S, I could take that ratio of S over the target margin of error, multiply by 2, then square it, and that's going to be approximately the sample size I would want to use for a confidence interval. If you, yeah, any questions about that idea? Okay, so I think let's move on to talk about not the binomial distribution, but rather the number pi that's the center of the binomial distribution. If you have xi distributed, a binomial, n and pi as the actual rate of success, I guess p hat, your sample proportion. Maybe I'm going to remove the I, just X. There we go. Okay, come on. This is something that was not working earlier today. Okay, so P hat would be then just X over N, the number of successes you get divided by the number of trials. And that's going to be a good way of estimating pi. At least we would believe so. The expected value of P hat is just, well, pi, okay, for reasons that we talked about a chapter or two ago. And so pi estimated by P hat, no problem. We're happy with that. What about a confidence interval? Our book has in chapter 7, section 3, a collection of large sample confidence intervals. The first one that we're going to tackle is a confidence interval for an unknown population rate, an unknown population proportion pi. So effectively something like this. I'm going to flip a coin 100 times. I'm going to calculate the proportion of heads in my sample, and I want to add a margin of error to that sample proportion to get a confidence interval for the actual population rate of heads. And you might think, well, it's always 50-50. Well, actually, no, it's not. I might have mentioned earlier this term, the Greek euro coin. If you stand it on its end and flick it and it spins around, it comes up heads far less than 50% of the time. It's closer to a quarter or a third. A quarter. It's about the size of a quarter. It comes up heads less than a third of the time, more than 20% of the time. The exact rate of heads on a Greek euro is unknown. So you find a Greek euro and you're going to spin it 100 times and figure out the proportion of heads that you're going to get. Excuse me. So you might very well go with P hat, the sample rate. But the way we get to a confidence interval is to start with a probability statement. The chance that negative 1.96 up to, and I'm going to go with 95% confidence here, less than or equal to the sample proportion minus the actual population rate, pi, which is unknown, divide through by pi times 1 minus pi all over n. And that's a number which we could sort of backtrack. If you want to talk to me in office hours about it, we could sort of show you exactly where in the normal approximation of the Poisson or the normal the binomial distribution where you could find the pi times 1 minus pi over n. But this is a probability statement, and it's like a 0.95. So 95% chance that, if you will, this thing here that's pretty close to z is in the negative to positive 1.96 range. Okay, so what do we do? Well, I think what we can do is sort of work backwards and solve for a range of plausible values. And due to the quadratic equation, when we get rid of the squaring here and then do the solve, our book walks us through it. I'm going to sort of jump to an approximate answer. The probability that P, actually, hold on a second. I'm going to rewrite this a little bit differently. How do I want to do this? We're going to define P tilde as X plus 2 over N plus 4. Okay. X plus 2 over N plus 4. How do we think of that? So if X is the number of heads that we get when spinning our Greek euro, you're just going to add to it, add 2 to the number of heads, and we're going to divide through the number of spins, divide through by the number of spins plus 4. So it's like adding in 2 fake successes and 2 faked failures. 2 heads and 2 tails will be added into the data. We're adding in faked data in some sense here, but the chance that, okay, P tilde minus 1.96, okay, times then P tilde times 1 minus P tilde all over N plus 4 less than or equal to pi less than or equal to P tilde plus 1.96 times the root of P tilde times 1 minus p tilde over n plus 4. That's 0.95. Actually, it's approximately 0.95. Actually, there's a sort of a guy in our stats department, Jimmy Doy, one of the authors of our textbook here, who in his work in graduate school, he went down and tried for a variety of contexts. In the actual binomial distribution, there are some combinations of n and pi where the approximation is actually pretty poor. But in most cases, we're pretty close. The upshot really here is if you add in these two fake successes and two fake failures and calculate this artificial biased, okay, estimator p tilde, if you go from p tilde down to standard errors and up to standard errors, then we are 95% sure to have pi in that range. The range itself is random. The range is going to be a little lower or a little higher, but 95% of the time, we will have captured the unknown true value pi. So the example I like to use in class, because it relates to my own life and it's sort of a fun little example, is you might remember the show Iron Chef. At this point in time, if it was an actual real life classroom, there would be like 2 or 3 students in the back nodding, yeah, I remember that show when I was a kid. Okay. So my own kid, Christopher, when he was about 5, we would watch Iron Chef. Christopher's now like, geez, how old is he? Oh, yeah, he's gonna be 29. No, he freaking is 29. So this guy is 29. He's like 9 years older than a lot of y'all. He watched this show at one point in time when he was a kid. And when we watch one episode of the show, well, okay, so here's the quick summary of what happens in the show. They tell you the secret ingredient of the day on this cooking network show, and the chefs they run over and grab the secret ingredient, and then they start cooking with it immediately because they have like half an hour to cook a 4-course meal. This guy, when he found out it was octopus was the secret ingredient, he ran over to this tank, pulled out an octopus, and immediately just cut the thing's head off and toss the tentacles into some breading, and the thing would be rolling around and self-breading, if you will. But my kid ran around the table many times. He cut his head off. He cut his head off. He cut his head off. So he's very excited about it. The name of that one Iron Chef, Morimoto, famous guy. He has his own line of knives that are supposed to be good. The upshot is this guy Morimoto, he's a specialist at seafood. How often does he win? What is the rate of this guy Morimoto actually winning? Okay, so if we see a total of n equals 6 of these battles, if you will, so n is 6, n is 6, okay, and x itself is 6. So in other words, he wins every time. Okay. His actual rate of winning, p hat, is just x over n, 6 over 6. It's 1. He wins like 100% of the time. But clearly that's not going to be a perfect estimator because he might lose sometimes. Our approach p tilde here says, okay, what we're going to do is just take our number of actual wins, 6, and going to add 2 to that. And then number of trials, 6 plus 4, well, 2 wins and 2 losses. Okay, so 4 additional trials. That's going to be 0.8. P tilde is 0.8. We're betting on 0.8. And if we go 0.8 plus a margin of error, we're likely to contain the actual true rate of success. Okay, and so our procedure says P tilde plus or minus, and I'm going to just go with 2 for now, times the root of, okay, p tilde times 1 minus p tilde over n plus 4, okay? And that's going to be hopefully easy to calculate. This will be 0.8 plus or minus twice the root of 0.8 times 0.2 over 10. That's 0.16 over 10, 0.016. I bet you we could do a calculator here and get the answer, but ultimately this will be a range of values which are 95% sure to have captured the actual winning rate of this Morimoto chef. Anyone have zero point 0.2 times 0.8 over 10 and then take a root of that? Again, like 0.016. Root of 0.016, then double that. Okay. So if you don't call out the answer quickly, I'm thinking it's time to sort
Two
of move.
times the root of 8 times 0.2 over 10 is 0.2529.
Okay, so 0.8 plus or minus 0.25.
Yeah.
Okay, so I'm going to say 55% up to 1.05%. Or now shoot, 1.05 is the rate, 0.55, 55% to 105%. And that's going to be capped at 1.00. So you're 95% sure that this Morimoto guy will be winning 55 to 100% of the time. It's basically saying I'm not going to believe exactly the 6 out of 6 wins so far. There's no way I'm going to be able to sort of be confident and sort of like happy there. And I betcha if you were to take our equation here and set the margin of error equal to some target level E, you could even solve for N that will get you the right margin of error. That plus or minus 0.25 is pretty darn large. If I wanted to be a plus or minus 0.1, I would want a larger sample size. Okay. So yeah, we could solve for N, but of course it would revolve around knowing or having a good guess at the value of P tilde that I will be getting in the future. But I'm thinking, shoot, let's just use the 80% we got so far. There's nothing wrong with the information we have at this point in time. So any questions about the solving for our margin of error here, or perhaps finding a new, larger sample size?
Not about that. Sorry, can you go over once again why the P tilde is better to use than just P hat?
Okay, yeah, great question. I didn't sort of say it explicitly, but yeah, literally inside our probability statement on the previous slide, and our book walks you through it. If we start with the chance that the sample proportion is in a certain range, being 95%, like the Z value being between negative 1.96 and positive 1.96. If you solve for then ultimately a range of values that are likely to contain pi with 95% chance, if you will, you end up with the number of wins plus 1.96 squared over 2. And then the denominator would have a n plus 1.96 squared itself, and that's 3.84. We round to 2 and 4. Ultimately, it gives us better probability coverage. It's a closer to 95% rate of success. One other thing to note, John, I guess if you're talking x over n versus x plus 2 over n plus 4, if n is big, they're about the same. So it's in the smaller sample size cases that this P tilde approach is slightly biased. It's slightly closer to 0.5 than the unbiased estimator P hat is. It's going to have a better rate of coverage closer to the target 95%. I think I may have answered the question, John. Could you rephrase if you want?
Yeah, I think that got it.
Yeah, the ultimate upshot is we've got methods of estimating things, and here is the first situation where ultimately our book says solve for a range of values that is symmetrical that will capture pi with a certain rate of chance, 95%. And in the solution, we find out the central value in that range isn't exactly p hat. The central value, which is this number I've called p tilde, you could view it as a biased way of estimating pi, but the biased approach with the margin of error added in is going to, at least in probability, capture the truth at the right rate of occurrence. So yeah, p tilde, it's a biased estimator, but it has some good properties. Okay, any questions, other questions before moving further into 7.3? Okay. So in 7.3, we sort of then move into a situation where, well, what if we have two populations and we take a large sample from each? And in this population, I'm going to draw it this way. There's a number mu1, another standard deviation sigma 1 in the second population, which also not necessarily normal, mu2 and standard deviation sigma 2. And you're going to take a sample size N1 from the first population. And so let's go with N1, and I get X bar 1 and S1, and a sample size N2 taken independently from the second population. I'm going to get a sample mean X bar 2 and a second standard deviation S2. What do we do with that? Well, I guess if you want to know mu1, you have a confidence interval based on X bar 1. If you want to know mu2, you're going to get a confidence interval based on X bar 2. What if you want to estimate mu1 minus mu2? And the natural way to do that would be the first sample mean minus the second sample mean. Literally, the difference of the unbiased estimators, X bar 1 and X bar 2, is an unbiased estimate of mu1 minus mu2. If I want to know how much higher the first group's mean is than the second group's mean, take the difference of the first and second sample means, okay? But we should attach a margin of error to that. Now, I'm thinking a couple things. One of them is a summer term. I would love to present, and I would love to, in office hours, go through a discussion of why the standard error I'm going to show you is the right way to go, but I'm not going to do that. I'm just going to say, here is the standard error that I'm going to recommend using, okay? In office hours, again, I'm very happy to sort of go through the math that justifies the following approach, okay? My 95% confidence interval. And to be honest, 95% confidence. I'm usually going to write things in terms of plus or minus 2. You probably should use plus or minus Z alpha over 2 if you want. That's a little bit more precise. But I'm going to go with the quicker, easier, approximate way of thinking. Confidence interval for the difference of the two population means, literally how much higher is mu1 than mu2, is going to be X bar 1 minus X bar 2, plus or minus 2 standard errors. And the standard error is a measure of how closely the one sample mean minus the other sample mean is to the difference of the population means. I'm going to note that that is S1 squared over N1 plus S2 squared over N2. And if you're thinking you see something like a square root of two things that were separately squared, and if that looks familiar to you from the Pythagorean theorem, the answer is yes, it is. Sometimes this is referred to as the statistical Pythagorean theorem. And like the Pythagorean theorem, we've got the law of cosines. I guess c squared is a squared plus b squared minus 2ab times the cosine of angle C. If there's a lack of independence in your sampling procedures, if the sample of N1 and the sample of N2 are somehow correlated sampling methods where there's a lack of independence, we can adjust for it. But I'm saying typically you're going to sample from the one population of bolts, and then you sample from the other population of bolts, and you measure the hardness of the one group and the hardness of the other group, and you want to know how much harder the first group than the second group on average. You're going to do this independently in most cases. So our procedure is really easy. Yeah, I take my two separate sample means, take the difference and plus or minus about 2 standard errors. Now I want to show you how you could get this done inside JMP. So I'm going to sort of clear the screen. Any questions before I clear the screen? Okay. So I'm going to clear the screen and I'm going to sort of switch gears and find a data set that matches the situation that we're in here. And darn it, I have to move this so I can see everything. And okay, so there we go. Courses 312 and 2026 and class data. And let's go with what's a good example? So I don't know, I'm feeling like in a fishing mood, and we talked about the catfish earlier. And I don't even like fishing, but we've got data on these catfish collected in the James River in Richmond, Virginia, and slowly we're going to get the data here given to us. And there's these species of fish, CCF for channel, W catfish, W white, and then it looks as though the white catfish, at least that one, and then the flathead, they're all sort of zeroed out. In other words, like they're not going to be included. Let's also select the matching cells. Okay. And we're going to hide and exclude both. Boom. And so now we won't see them and they won't be included. And flathead and so blue. So the white, though, are only this. So I'm going to, again, select the matching cells and take all the white catfish and eliminate them from our analysis. Hide and exclude. There we go. And so what we've got is blue and channel that are left. If I want to know how much longer the blue catfish are than the channel catfish on average, the procedure is pretty darn straightforward. We even would see this really, yeah, shoot, I don't know, the lab walks you through it. Fit y by x, okay? Literally tell me, how does the length differ between the two species? Now, there are 4 species, but we're only dealing with 2 of them. I eliminated the rest of them. I click OK. And I see, oh, the blue catfish, where there's a wide variety of lengths. Okay. Channel catfish, again, wide variety of lengths. Here's like the average length across the species. If you just turn on this thing called, we'll see in a few minutes why it's called a T procedure. Okay. I'm going to turn on this T test. And it just lets you know, okay, literally, if your samples are both large in size, and we got hundreds of each, a difference of the channel catfish mean minus the blue catfish mean is like a -27. So the blue catfish on average, I'm sorry, are 26 millimeters longer on average than are the channels. Channel catfish on average are smaller by 26 millimeters. So that's like about that much. Okay, not too much, but we're 95% sure that the difference is in the range -16 to -36. Oh, let's rephrase that. 26 plus or minus 10 millimeters is about the difference of the 2 population means. I'm happy with that. If you are given the mean and the standard deviation and the sample size for each of the 2 groups, and the ends are both large and you have independent samples, you're home free. If you have data values in a software package like JMP, again, you're home free. The fit y by x should get you what you need. Okay. Any questions about the difference of the 2 population means in the large sample size situation? Okay, so then there's up to 2 more things that I want to mention. One of them is now in chapter 7, section 4. We're going to move in and talk about a small n estimate, or better yet, confidence interval in the normal population case. So sometimes you're thinking, okay, well, how often do we really know that the population is normal? And the answer is often you don't, but the normal population possibility is very alluring. And the reason is if your population is normal in shape, if the histogram of the values in the entire population follows a normal curve really well, even when the sample size is small, we're able to do exactly the confidence interval that you need to do. It starts with then without going into too much detail, I'll just say that the probability that your X bar minus the population mu over S over root of N, the chance that that's in the range, I'm going to call it negative T alpha over 2 up to T alpha over 2. That is 1 minus alpha as a chance. Okay, so you're thinking, what the hell is this T alpha? It's like the normal, it's like the Z. The slight difference is, notice that if we have in our denominator, we've got this S over the root N instead of sigma. If in fact we knew sigma, we would plug in sigma here happily, and those T values, well, they'd be called Z values and you're home free. Because there's some additional, okay, variability when we then additional variability when instead of dividing through by sigma over root n, we divide through by s over root n. S itself is itself a random variable. There's extra width, if you will, in that t interval. And clearly, if sigma is quite close to s, or s is, if you will, quite close to sigma, that happens when n is large. It doesn't matter. You call it a z. If s is based on a small sample size that you're willing to believe is from a normal population, call it a t. You're home free. Okay? So let's talk about finding a value t alpha over 2. I'm going to show you two different ways how to do that. Maybe I'll show you first the confidence interval that is implied by that. 100 times 1 minus alpha percent confidence interval for the unknown mean mu is X bar plus or minus T alpha over 2 times S over root of N. It's our same friend over here on the very right. That ratio, S over root N, is just the standard error that tells us how close X bar is likely to be to mu. And how much do we go up and down? Instead of Z, we're going to go up and down T. And that's a number that's going to be a little bit larger. It will still probably be close to 2 if N is large-ish. Okay, so let me show you how to get that T value a couple of different ways. One way is if you just literally go into the GMP probability distribution calculator, and let's download that. Okay, come on. I love it when the internet is slow sometimes and not others. So our JMP probability distribution calculator, super convenient for homework and stuff. I'm thinking just going to open it up and click OK. Yeah, okay. Instead of the normal curve, say, oh, no, T distribution. And you tell me what are termed degrees of freedom. I'll tell you about that in a little bit, but let's suppose for the no, and it's 10. If I want to get a 95% central area, it's 0.95, right? My T value would be plus or minus 2.2281 or minus 2.2281 standard errors. It's a number pretty close to T. If the degrees of freedom is something like 100, you're going to say, oh, look, that's pretty close to 1.96. It's literally 1.98. If the degrees of freedom were 1,000, it's really close to 1.96. But if degrees of freedom were only, shoot, that's not what I wanted. If it were only 3, my range of input probability, central probability 0.95. my T value with not 10 degrees of freedom, but 3 degrees of freedom would correspond to, okay. How did this not work? Okay, 3. Okay, seems like when I adjusted that, it didn't work nicely. I'm going to get back to open it again, instead of normal T. And if I wanted 3 degrees of freedom, yes, finally, central chance of being correct, 0.95. My central probability is going to correspond with a T value of like 3 plus or minus 3 standard errors. That's a lot larger than 2. It's because our denominator has an S in it, not sigma, the true population standard deviation. If we have to estimate S with sigma with only a few data points, we're in trouble. Okay. So what about this degrees of freedom? Okay. Our T distribution, degrees of freedom. Okay. So the degrees of freedom, df for the T distribution, is just the number of data points minus 1. And it relates to, remember when we have S, the standard deviation is 1 over n minus 1 times the sum of xi minus x bar squared. That denominator there is related to the T degrees of freedom. So basically, if you tell me the number of data points, subtract 1. And then that is going to be degrees of freedom that you'll be utilizing. So if we have n equals to, come on, let's go with n. Let's go with a different color for now. If n is 32, degrees of freedom would be 31. You would go into our GMP probability calculator and say, aha, 31 degrees of freedom. Boom. And if you want a central area, 95%, if you will, confidence interval, 95% chance that the range will cover, the randomly chosen range will cover mu is plus or minus, would you believe, 2 standard errors. The T value would be negative 2.04 or positive 2.04, or if you want to be more precise, 2.0395. That's why I round to 2 for 95% confidence. If you want middle 95% rate, whatever the degrees of freedom, as long as it's like 25 or higher, it's going to be pretty close to 2. So let's go for even 100, pretty close to 2. Okay, so my confidence interval procedure is based on T. T alpha over 2 is the T value with exactly alpha over 2 in the upper and the lower tail. The rate of error of 0.05, it's going to be 0.025 in each of the tails, 0.025, 0.95 in that middling zone. Okay, so let me show you also how you could get with the T table the exact same T value. That T table, I'm just going to open it up here, and this is what I would encourage you to bring to the final exam, just because that way you'll be able to have it lying around, because if you don't feel comfortable using just 2, our T table, and this is just one way of formulating the T table. It says how confident you want to be. Oh, 95%. Just use the number in this column. And if you had degrees of freedom was 31, well, we don't have 31. I could use 30 degrees of freedom. I could use a T value of 2.042 because that corresponds to 30 degrees of freedom and 95% confidence. Here's a thought. If you have degrees of freedom and you're working with a T table, which doesn't give you all the possible degrees of freedom, round down, literally use a higher row. If I had 39 degrees of freedom, instead of using 40 degrees of freedom and therefore a T of 2.021, I would round down to 30 and use a 2.042. Would I still be using about the same value? Yeah. Always round degrees of freedom down. It's a little bit safer. It will give you a slightly wider confidence interval by a hair, just a hair. Okay, so that's a good place to sort of wrap it up. I do want to note that the lab today corresponds to not exactly what we did, but the last section in chapter 7, section 5, a confidence interval for the difference of mu1 and mu2. We sort of saw that already, but we saw the large sample case. What if your samples are not large in size, but are rather small in size? What should you do? Gut feeling is the difference of the sample means would be involved. Plus or minus how much? Well, it's probably going to look like s squared over n plus the other s squared over its n, then with a root times a t value. The difficulty is getting that exact t. But hey, the lab walks you through it, and probably JMP does it for you for cheap. In other words, not a lot of effort if you have the software and raw data. Okay, good place. I'm going to sort of hang out for a few minutes, and then office hours will start up in 10. If you have any questions, just hold on for a little bit, but I'm going to stop the recording after the questions disappear or they become non-related to the subject. And office hours again start in 10 on the nose. We'll see y'all soon.